All right, let's talk about the correlation coefficient, which is also known as Pearson's correlation coefficient. We denote it with an R. We've seen this before in Algebra 2. Where R is always between the numbers -1 and +1. There could be any decimal between -1 and 1, but it can't be beyond that. Kind of like a percentage. You can't be more than 100%. You can't be more than 1. The correlation coefficient, though, can be negative. We talked in the last section actually already about how a correlation can be negative if the slope of its line of best fit is negative, like decreasing from left to right. So let's just start there. The correlation coefficient, R. The first thing we're going to do is actually just estimate it. There's a way we can calculate it. But if you're given a scatter plot and you're just asked to estimate what you think R might be, which we did in Algebra 2, this is what you would do. I'll give you kind of an array of different possibilities here for different scatter plots. I'm going to draw 5. Okay, so let's start with -1. If R equals -1, that means we have a negative slope and a perfect straight line. Okay, if our correlation coefficient is exactly 1 or exactly -1, that means that our data fits perfectly on the line. Every single point is on the same line. So that could look like, oh, I want a negative. That could look like that. Okay, so I can definitely draw a line that goes through all of those points perfectly. Okay, if it's spread out at all, it's no longer going to be a perfect one or a perfect -1. So let's see, +1. R equals a +1. Again, it's going to be a perfect line, but now it's going to have a positive slope. So I'll just start here and draw points going in a perfectly straight line with any slope, as long as it's a positive slope, R equals 1. Okay, and then in the middle, of course, right between the two, R equals 0. So if the correlation coefficient equals 0, or the correlation is none, think about the last section. When something is not correlated, when there's no correlation, that means your data is just so spread out and all over the place that your two variables really aren't related at all. Okay, so that would be no correlation. Okay, and then everything else is kind of between that. Okay, R equals a -0.5, -0.5. That means we have a negative slope left to right. It's kind of going down left to right, but our data is pretty spread out here at 0.5. I'll just kind of draw negative, very spread out there. Okay, and the same thing for a positive 0.5. It's going to be increasing left to right, but be pretty spread out at 0.5. Okay, I might even make it a little closer than that. Okay, so we can kind of guesstimate from there. The more spread it out is, the closer it is to 0. The closer it is to a line, the closer it is to either positive or -1. Okay, next, we can actually use a graphing calculator to find the actual correlation coefficient, like exact number. And you've actually already done this before. When you did your linear regression, when you went to, it was option, it was stat, move over to calculate. Option 8 was this linreg, a plus bx. We use this to find our least squares regression line in the last section. And I told you not to worry about those last two numbers yet. Well, now we're looking at those last two numbers. So, and the one that's really truly important is the last one, R. R is the correlation coefficient. So in this case, for this line, they put in this data, 1, 2, 6, 5, 4, 3, and it gave us this line here with this correlation coefficient. So R, our correlation coefficient, is approximately, because we have to round, -0. I'll leave 3 decimals, 5959. or 945, I meant to put 945 is the correlation coefficient. So again, anytime you round, make sure you put approximately. And from this correlation coefficient, I can see that the slope of my line of best fit is definitely going to be negative. In fact, we can see that here, that it is negative. So it's decreasing left to right in general, and this is very close to -1, right? Negative 0.94 is only like 600 away from a perfectly straight negative line. So this is a very strong negative linear correlation, okay? In fact, I'll write that. This is a strong negative linear correlation here. All right. So the next thing is symmetry of R. So it turns out, remember how we talked about in the last few sections about the explanatory variable, the response variable, and how we can really label them either way. It just depends on what we're wanting to measure or what we're wanting to compare or make predictions of. So if I needed to switch out my X and my Y, like if I had distance relating to time and I wanted to switch it up so that time was relating to distance. So if we interchange our X and Y values, the correlation coefficient is actually unaffected. Okay, so this makes sense too, because if you think about it, when you interchange your X and your Y values in a graph, all it does is actually reflect all of the points over the diagonal line Y equals X. And when you're reflecting something, you're not actually changing the size of anything, and therefore the size of your residuals is unaffected. So your points are not moving any further or closer to your line of best fit. So it's just as closely related as they were before. So your correlation coefficient won't change. It'll be the exact same number. Next thing on here is the actual formula for the correlation coefficient R. You aren't actually going to have to use this. They just want to show you and make sure that you understand it. Oops. So just so that you know, where's my pen? The formula for R here, it's actually the mean of the product. Oh, wait. The dialog box in my way. It won't go away. The mean of the product of the standardized X and Y values. So you can actually see that here, the X values minus their means divided by their standard deviations, that actually is the standardized X values. And this here means that we're adding all of these together. So this is every single X value standardized. And over here we have the same thing for our Y values. So every single Y value standardized. We're taking each of those standardized values and multiplying them together. So we get the product. And we're adding all of those products together and then dividing by almost the number within the set. And this is just like with the sample standard deviation, where we don't quite divide by n to account for error in sampling. So this gives us the mean of all of the products of all of the standardized X and Y values, all their Z-scores. And that ends up being R, correlation coefficient. So again, you're not going to have to use this formula exactly. They just wanted to show it to you. Another way that we can look at the correlation coefficient R is like this. It turns out that correlation coefficient, the slope of your line of best fit, and the standard deviations of your two variables are all related in this way. Okay, so B1, remember, is the slope. R is a correlation coefficient. This is the standard deviation of your response variable, Y. And this is the standard deviation of your explanatory variable, X. So look at this example here. It says compute R for this data set. So I can plug the data that we have into that equation and I should be able to find R. Okay, so let's see. All right, so the first thing you should notice on here actually is that we don't have B1, we have B naught. So remember, B naught is the y-intercept, B1 is the slope. Another thing to know on here, remember y bar, that's the mean, the sample mean of the y values, and x bar, this is the sample mean of the x values. So there is actually a relationship between the slope, the y-intercept, and any points on the lines. And the sample mean and the sample mean of either variable is on the line of best fit, the least squares regression line. So the relationship here, and actually I need to add this to your notes, is B naught, the y-intercept, will always be equal to y bar minus B1 times x bar. So I can use that, plug in what we have here to find B1 because I need that first of all. So B naught is 1, y bar is 7, B1 we don't know, and x bar is 6. And then we should be able to solve for B1. So I'll subtract 7 from both sides. Divide both sides by -6. And we find that B1, our slope, is actually 1. And I'll add that over here to our statistics. Okay, and then I can use B1 and these sample standard deviations that are given to me to find R. So B1 equals R times the sample standard deviation of Y over the sample standard deviation of X. B1 is 1, R we don't know, SY is 3.1, SX is 2.5. So I have R times this fraction, and I can go ahead and grab a calculator and get that fraction. 3.1 divided by 2.5 is 1.24. So 1 equals R times 1.24, or 1.24R. So divide both sides by 1.24. 1 divided by 1.24 is about 0. Here, I'll write the whole thing. It's 0.80645161129. I would say R is about 0.806. Okay, so while calculating the correlation coefficient using the formula is pretty long and complex and you're not going to be asked to do it, it's actually pretty quick to find it if you do know the slope and the standard deviations of your variables. Okay? And the last thing on here, again, remember we're talking about correlation coefficients. We're talking about how strong these correlations are, but always, always remember that correlation does not imply causation. Okay, it is possible for two variables to have a very strong linear relationship, but actually not be related at all. So they're going to ask you about cause and effect. They're going to ask you, does this cause that? Is the correlation strong enough that we can say that this causes that? We can never say that something causes another thing unless we perform scientific experiment. Okay, and we'll talk more about experiments later on in this class, not yet. So as of yet, unless an experiment, an actual scientific experiment has been performed, we cannot talk about cause